समस्ती कंडू का तो बहुत बड़ा हो गया। राजदीप तो कहा लिया था सर। घंटा जान।
Hello, Mr. Mulugeta. I am Mujahid Hussain. Sir, you are not audible. Voice is not coming to us. It is mute at your end, I think.
Yeah. Okay.
Yeah. Yes.
Now,
Yes.
yeah,
Now it is audible. Now it is audible.
Yeah, it was the mic was muted. Okay.
Yes.
Okay.
So welcome in our conference, sir.
Yeah, thank you very much.
And how are you?
I am fine. And you?
I am also fine. And thank you very much that you have spared your precious time for us.
It's my pleasure. Thank you very much also for inviting me. I was so busy and didn't attend your all sessions. I'm sorry. I hope it was interesting. I hope so.
We are connecting everything on YouTube also.
Okay.
And Facebook also. We are making it live.
Okay. It's okay.
So you are at the final stage of submission of PhD.
Yeah, I will submit within this 1 or 2 weeks, this month.
Oh, then it's really very busy, and then also you have to spare time for us. So really thankful to you.
I like to attend, but I cannot. It was very hard for me.
Yes.
Yeah. So just I spent like 5 years in research for the PhD, and I was participating in so many conferences in Europe. Just you can go in 28 countries in Europe if you have this Schengen visa. Yeah, it was very easy for me here. So within the last 1.5 year, I just ignore any conference because I became busy. So when my friends informed me, just I said okay for this.
Yes, Mr. Akash Ingle.
Yeah.
He's my student actually.
Yeah, just we had one chapter and one paper together. We published one book chapter and one paper together. Yeah. And also Dr. Kapil Kumar Ing. Do you know him?
No.
Okay. Yeah, we have another friend. He was here. Now he's in one research institute in India. He was my friend here. We were living together here. But actually, Akashi, I know only in Skype and like in Zoom. We don't know each other.
Achha, that's. Actually, we have to start at 12:30. We will wait for 2-3 minutes.
Yeah. Okay. So I will share my screen, or what will I do? I don't know.
You can share, sir. We will transfer the controls to you. You can share it.
Can you see like this? For example, like this?
For example?
You cannot. Can you see my PowerPoint, my PPTs?
Yes, sir, we can see it. You will have to share it.
I have to share it, yeah?
Yeah, and we'll transfer the controls towards you.
Given the control.
Controls are already given, so you can share it.
On Zoom?
Yes, on Zoom.
Okay, firstly, I have to share, yeah?
Yes. There is a green color menu given, I think, at the bottom.
Yeah, because the Zoom and the PowerPoints are separate. That's why I'm asking you. Okay, let me share and try it, yeah?
Before starting, I will give an introduction of yours. I will read your biodata at 12:30.
Okay.
And then, then the sharing will be done.
Okay. That's good.
I have seen your biodata. Actually, you are working as a teacher in Ethiopia, no?
Yeah.
On deputation basis, your country has sponsored you for research.
Sorry?
Your country has sponsored you for research at Hungary. At
Your
Hungary, you are doing PhD at Hungary, no?
Yeah.
It is on deputation basis.
What do you mean reputation?
You have been sponsored by the country.
Yeah. There is a scholarship for worldwide scholarship from the Hungarian government, which is sponsored by the European Union. So I have a sponsorship, yes.
Yeah.
For 5 years.
Yes.
Yeah. But I have a job in Ethiopia. Yeah. I was working there with masters, but now I will go back again within this month. Just after 3 weeks, I have to go back to Ethiopia for my position.
Yeah.
So I will defend on February or March online with Zoom again, my thesis. So my paperwork and everything is already completed.
Yes.
Yeah. Okay.
So our best wishes are there. So you complete your PhD work as early as possible and get a degree.
Yeah. Yeah, it's possible.
So I think it is 12:30. So I will start the session. I will first read the biodata of Mr. Mulugeta Fenta, who is the speaker of today's session. Mr. Mulugeta Fenta is a research scholar at CZ University, Hungary. He is an MSc in Earth Science and is doing his PhD in Geoscience. He works in the field of geotourism, application of GIS and remote sensing in Earth Science, GIS fieldwork, advanced modeling in GIS, fractured reservoirs, remote sensing of latest technology, big data mining for geoinformatics, shallow geophysical field surveys, subsurface fluid flow systems, geothermal energy utilization, sedimentary geology and processes, crystalline basement of STIZA mega unit, technologies of reservoir simulation, environmental geology, and analytical techniques in environmental geochemistry. So basically, he is a main of geology and remote sensing. He is working as a teacher in Bahir Dar University School of Earth Sciences, Ethiopia. He has got several good publications in his credit and he has attended several conferences. So this was the brief introduction of Mr. Fenta Mulugeta, who is soon going to submit his PhD at Hungary. So I request sir to have a dialogue with our audience. Welcome, sir.
Thank you very much, dear professor, and thank you very much for your invitation. And hello, everyone. I cannot see anyone. Okay. Thank you. So I will share and continue my session. So my today's talk is sorry, about geophysics and its benefit for humanity. Can you see my PowerPoint? Sorry.
Yes, it is visible.
Okay.
Make it full screen. I think you can make it full screen also.
Okay. Yeah, just for confirmation. Yeah.
Yes. It is visible.
Okay. Thank you. So my talk is about geophysics and its benefits for humanity. So I would like to introduce first about geophysics and its benefit. And later, I will take one case study of my previous study from southern Ethiopia in East Africa, and I will talk about that, how geophysics is beneficial for humanity or for permanent settlements of people. So, as an introduction, what geophysics is? Geophysics uses simple physics principles and attempts to solve several social and economical problems, which means that we can use geophysics and we can solve various social and economical problems. And it's like applied science, like other applied sciences, and it uses simple physics, some principles, and it studies Earth's structure and explores its economical valuable resources. We know that Earth has several valuable resources which are very important for our economical development. So geophysics uses the physics principle and explores those resources and manage wisely for the economic development of a country. So, so simply, geophysics applies some principles, maybe very simple physics like high school physics, what we know in high school, but its application is really important that it can change the country's economy. Or it can solve like human crisis, like such as shortage of groundwater or fresh water, the fresh drinking water, or it can explore, we can use that and explore valuable earth resources like crude oil, petroleum, which is very important and a worldwide issue now, and also gold and diamond, very precious resources also. These all uses geophysics for exploration, because we cannot get them easily from the earth and we cannot see them by our naked eye, so that we will use simple physics and explore them from the ground. And when we extract them from the ground, then it will have a very good economic impact for the country. So, or we can use the geophysics to study the environment, or to study, to solve some humanitarian crisis like shortage of water, cleaning, so many things. So what are the basic principles which we can apply from physics? Like we can apply like universal gravitational law, very simple physics. Like we can apply like Newton's second law of motion, or we can apply like Snell's law in geometrical optics, or we can apply like Ohm's law in electricity, which are very simple and what we know in high school and before university. But these principles are really important, and it can change the economy of a given country if we apply carefully and if we follow certain procedures and explore Earth's resource for our economic development. The question is, how can we apply? So in order to apply these principles, there are well-developed techniques. And these techniques are called geophysical techniques. And the geophysical techniques can use a single physics principle, or it can use combination of physics principles. Some of the geophysical techniques use simple geophysics or single geophysical principle or law, or it can use like a combination of geophysical principles. So the methods uses like the geophysical methods, which uses simple physics principles to explore the Earth's resources. It uses like basic principle first, and then it uses instrument. There are also developed instruments to take survey on Earth. And again, after using an instrument and then data collection, we have to conduct a survey on Earth, and then we have to process that data, perform certain modelings, corrections, and change the number which we collect using the instrument into economically valuable resource. That is the procedure. So it needs, of course, it requires experience and a lot of knowledge, of course. Now the procedure, but the principles are very simple, and everyone in natural science knows the basic principles in physics, what we can apply in geophysics and explore Earth's resources, very valuable and economically useful resources for any country's development. Then, if I say this as an introduction, so now I would like to present my case study of application of physics to solve some humanitarian crisis in southern Ethiopia. How I apply, I use 3 types of geophysical techniques and apply like a gravity, magnetic, and electricity for groundwater exploration. So the area was very semi-desert, and the people were there nomads, and they don't have fresh water supply. So there was a very humanitarian conflict, and there was some ethnic conflict due to water. and they have to travel long distance with their animal to fetch water. So I use 3 types of geophysical techniques to explore the groundwater, and to solve the humanitarian crisis in the semi-desert area of southern Ethiopia. So the basic principle is what I used was the universal gravitational law from physics, Newton's second law, again from physics, and another simple law, which is Ohm's law, and then the magnetic force. Now I use these basic physics principles, and then the geophysical methods, I select geophysical methods which uses this basic principle, and can apply for groundwater exploration. So let me say something about the area where the case study is performed. Now, the area is located in the southern Ethiopia here, very close to Kenya border. I hope most of you guys know about where is Ethiopia. It's in East Africa, close to Indian Ocean, maybe. So my research was just southern Ethiopia, very close to northern Kenyan border. So this is the elevation map, and this is a topographic map or elevation map. So the area is like semi-desert. It has some rainfall, but the rainfall is really low rainfall, and there was no any river or spring or other form of surface water for the cattle and the people to have water. So they depend on seasonal rainfall. So the people, they have to travel long distance to have water when there is a fluctuation of rainfall. So people just, if you see the photos, this is the photo taken from the area. So they have to travel long distance with their cattle to fetch water. So this was a very hard area to have a permanent settlement for the people. And sometimes when they collect rainwater, the rainwater was the source of conflict between the people who lives in that area, because they need it, and it's a very basic need for them. Then, when we see the climatic condition of the area, it's arid to semi-arid climate condition with 2 rainy seasons. And the main rainy season is from March to May, but sometimes there may be short rainy season from September to November. And rarely the area can get some rains from June to August. But this December and January are the hottest months. It's opposite of the northern hemisphere. Where I'm living here, the December and January is a very cold and rainy season. But in the area where the case study has performed, it's the most dry season, dry months or dry season. So when we see the vegetation cover, the area has such types of vegetation. It's very mostly continuous, dense and tall grasses with thorny shrub and wild seasonal and scattered small trees. So these trees will be green area when there is rain, and it will be like dry in the dry seasons without any leaves. Then, if you see animals, there will be like it looks like a savanna land with grasses during rainy season, and it will be very dry during dry season like this. So there are also wild animals like ostrich and domestic animals like this. So they have to have rain or some source of water to have settled lives. So during my survey, there was no any infrastructure to conduct survey. So I have to go crossing so many obstacles, like no telephone, no electricity, no bank, no health service, and then you have to drive through these weather roads. So there is no any telephone something. Then during survey, we have the probability to lost our position. So we usually use GPS. No phone, nothing. We cannot call anyone. Then if you lost, that's all, lost in the area. So you may, we had a possibility to to stay there maybe a week if we cannot get the way how to out and join the main roads. So it was very challenging, but a very necessary work to have a permanent settlement for the people, because water is everything in the area. Then drilling a borehole is crucial for the area, as there are no any rivers, streams, or spring in the area to have water. Then what can water help for the people? It's very new that the water can help for the people to establish schools, because they don't have school, to have healthy centers, because the people are not stable life, they don't have stable life, so it's not possible to have healthy centers. And then if there is water again, they will start stable life around the water. If they have water, they will be stable. And then reduce frequent hunger exposure and reduce waterborne disease, of course. Avoid conflicts due to shortage of water, because water is the main source of conflict. And then improve quality of life and improve livestock products in quality and quantity, and also preserve wildlife. Then water is very crucial resource in the area. Then what I did was, first I studied the geology, because the geology is the main one which reserves the water. So I start to assess what type of rocks are there. And then I have got that the area is totally covered by volcanic plains or volcanic rocks, and beneath that there's a basement rocks. Then the basement rock is bandedness. I don't know, maybe you have some geology or science background or not, I don't know. Maybe hard to understand who comes from social science and humanity. But I hope the natural science and engineering or technologies, they will understand what I'm talking about. And then the volcanics includes like vesicular basalt, scoria, and there are also recent alluvial and illuvial soil deposits. Now, within this background, I map the area, the geological map, and prepare the geological maps. And in the geological map, I can see some structures, some fractures, cracks, and others which can serve as a conduit for the water beneath the surface of the earth. Now, with this in mind, I cannot recommend any place to drill a borehole, because I don't know, I don't have any information where will be groundwater. That was the main question. Plus to that, like this, the area, you cannot travel, you cannot go anywhere just as you want, because the area is very very hard. Like it has a lot of rocks, like scoriaceous rocks like this. You cannot drive. In this case, you have to go by foot. And the area has also bandedness like this. And when we came to the geology, I realized that the groundwater will be in the porosity and the cracks and vesicles of the rocks, and in the volcanic rock, and again in the basement rocks, it will be in the fractured and weathered part of the rock. Then with this information, I have got again another information that there are 3 boreholes already drilled before my research, and that was very good input for me. And one of the borehole has 5.6 liters per second, but the other 2 boreholes were dry. So my research was expected to explain why these boreholes become dry and why this borehole has only 5.6 liters per second. And the boreholes, their depth extends from 200 to 350 meters below the surface. Now, when I see from these boreholes, the water-bearing layers are highly weathered and fractured quaternary vesicular basalts, and weathered and fractured upper part of basement rock, which is nice, and the gravel deposits. So my search was to focus up to the upper part of the basement rock, because after the weathered and fractured part of the basement rock, I realized that I cannot get any water. Then within this information, I applied 3 types of geophysical techniques: gravity, magnetic, and resistivity. Both of them use simple physics principles, and they have also corresponding geophysical instruments to collect data on the ground. Then, the main aim of the base or the resistivity survey, corresponding to resistivity, which is called vertical electrical sounding. The main survey was to locate groundwater potential areas, which means the resistivity survey will show me where will be the water or the groundwater potential areas and determine the depth at which the aquifers are located. So, which means if I conduct resistivity survey, I can know that, or I can estimate the depth to the water, and I can estimate also good potential. I can delineate also good groundwater potential areas for drilling. Okay, but this was not enough. Then I applied gravity again to map the basement topography. The basement topography, because below the basement, I realized that I cannot get more water. Then, because of this is volcanic rock, I realized that water can be stored in fractured and weathered, in fractured parts of the volcanics. And then I applied magnetic survey to map the structures which can be a possible conduit and storage of groundwater. Then I use these equipments. This is a resistivity meter, which measures the resistivity of the ground. And then with these equipments and the survey, I collect 28 resistivity, I collect resistivity data at 28 points. And then there is gravity, because for each geophysical techniques, there are different, there are corresponding geophysical equipments. And this one is a gravity meter, which measures the Earth's gravitational. And then this is GPS, which is helpful for the data processing of the gravity data. This is a differential GPS. It measures location. And I use this location data for gravity reduction, because the geophysical data, they need a lot of processing before changing into geology. So in field, for 17 days, I did these surveys. And again, I collect magnetic data using the GSM 19T magnetometer, because I applied 3 types of geophysical techniques. So I have to use 3 different types of geophysical instruments. Now you can imagine how much it is very tiresome, but the objective was crucial, because we need water, which is very important for the people, and that can solve the human, that can solve the problem of the people there. Then these are the points where the magnetic and the gravity data are collected. So I distribute my data points here like this. The red ones are for gravity, and the blue ones are for magnetic data locations. So I collect 450 magnetic points, which means magnetic data at 450 points. And I collect gravity data, these red points, at 115 gravity, 150 locations. Now, again, for the third type of geophysical technique, I collect again 28 resistivity data at 28 points again, and I distribute in this way in my area. Now, when I conduct the survey, I know that there were 3. I have 3 boreholes. This one, and this one. These are boreholes, and this were dry, and this was productive, which has 5.6 liters per second. So my survey was also expected to explain why these boreholes become dry. Whoever, I don't know who conducts that, but whoever conducts the survey, the result is that these boreholes were dry. Now this borehole has 5.6 liters per second, but the yield is not enough for the people, as there is no any river or spring which can use for the people and their cattle as a freshwater supply. Then my next step was to process again, because this data collection was not enough. So I have to do a lot of processings, modelings, reductions, corrections, and then change into map and model sections, which can be interpreted into geological term and which can locate the presence and absence of groundwater. Because my aim was to locate the groundwater where it is and then to recommend for drilling. Then I did several processings. I cannot present the details of each because it's very broad topics. So just I can introduce you like a lecture, the highlights of these things, not the details of this. So I did processings for the magnetic data, for the differential global positioning system or DGPS data, for the gravity data, and for the vertical electrical sounding data. Because after data collection, then what comes is just processing. So after I filter all data using softwares and sometimes programming languages we may use, or sometimes we may use already written scripts. And then other written instructions, or we can use also other written instructions and apply to remove all unwanted data and left causes due to geology. Then if we remove all unwanted data and if we correct and process the data, then the remaining response of our survey, the remaining result will be caused by the geology. Then we can change that, we can interpret that geology and we can estimate where is the groundwater. Then after processing, I present my results in terms of profile plot or model sections or maps, different maps, 2D and 3D maps, and again, stacked profile plots. Then from the profile plots and the model sections, or from the maps, 2D or 3D maps, it was possible for me to interpret where is the water, and it was possible for me to locate the borehole drilling sites. Then the first, from these results, it was possible for me to interpret qualitatively and quantitatively. When I say qualitatively, just relative things, and quantitatively using number and in quantities, which means the depth and the quantity or the estimation of groundwater yield. But for say qualitative, just we can say relative to this area is good, this area is potential, like that. So the combined interpretation of all geophysical techniques, including geological informations, which means the previously drilled boreholes and other hydrogeological informations, then I start to interpret with this all informations, then I start to interpret the area from surface topography. Now, using the maps, now I start the interpretation. Now, when I see the surface topography or topography map, now I can realize that, okay, to the west, the western side of the area, okay, it's lowland, and in here it's relatively highland. Well, because it can help me to estimate in what direction can groundwater flow. Then next one, I use the gravity map, and one of the gravity results, which is called free area anomaly, shows me almost similar to the topography map. Just it has low values, the west, south, northwest, and southwest, and it has high values to the east. Okay. Now, within this, bearing this in mind, I have to reduce again and remove some processing from this gravity data, and I have to try to reflect the response of shallow geological materials. And then I produce this simple Booger anomaly map, which is again produced from gravity, but this one shows me low value in the northeast and southern parts. Now, again, I process and use another gravity map, which is called residual gravity anomaly, but this one shows me all the northern part and some parts of the southern part of my area has low gravity anomaly maps. Now, again, I process the data and I have got another map which can reflect the shallow depth geological materials. What I want is shallow depths because my drilling will not extend more than 350 meters. Then, when I process the gravity data, I have got this type of map, which is called residual gravity anomaly map, having at this area low gravity and at this area low gravity, which means that this area there is something less dense objects, and in this area there is something less dense objects, and these less dense objects may be water. It can be water or it cannot be water. It cannot tell me the presence and absence of water. But what I can understand from here is there is a less dense object, and in here very high density object. And this high density object can be basalt without any fracture and without any water within it. But this less dense object can be very fractured and vesicular with a lot of pore spaces, and may be filled with air or water, which causes to be less dense. Then within this idea, within this result, I went to the other geophysical techniques because I need more information before recommending for drilling. As drilling causes loss of money and time and also equipment. Then I use the magnetic data and I prepare this map. And then from this map, I can see here is the low magnetic values, low total magnetic values, and here are high magnetic values. But I can see the patterns. There is a pattern here, and there is a pattern here, and there is a pattern here, and this pattern here. Now these alignments are caused by geologic materials beneath the surface, and now I can estimate the fractures from magnetic data, magnetic survey results as based on my objective. Then again, I reduce one more, I process one more for the magnetic data to have the shallow effect, only to map the shallow subsurface effects. Then I have got these types of maps. Now I can trace, I can realize here is one trend, another trend, another trend, another trend. Now my aim was, for magnetic survey, my aim was to map possible structures which can be used as groundwater conduit and storage. Then I can infer some structures from here. And from the gravity map, I can say that the basement topography here is at higher depths because it's low density here, which means the basement, which is the gneiss or the metamorphic rock, is high density. Then the distance of the metamorphic rock from the surface in here is very high, which means that this rock can have a high, at this place, the geology or the subsurface rocks can have a good, can be a good potential or can be a good storage for groundwater. And again, from this, I can map some structures. And then I inferred from magnetic data these types of structures. Now, I assume there is one structure like this, the red ones, and assume another structure like this, another one like this, another one like this. Now I have two things. One, structure which can be used as a conduit and storage for groundwater. And two, I have one information from, very good information from gravity maps that the basement rock at this point and at this area, and at this area is found at higher depths. Now I have to combine these two things, but still I cannot say, even though the basement rock is at higher depths at this place and this place, I cannot say that this place has water and this place has water, or this place has not water. But I can see this place has, the basement rock at this place is less depths. And in here, it not only the basement rock, but there is another rock which has higher density object. So the probability of getting water in this area is very low. Then I have to use the third technique again, which is resistivity. So the resistivity technique depends on, the resistivity response depends on the presence and absence of water beneath the surface. Because resistivity, the resistivity survey sends some signal. When I conduct a resistivity survey, I have to send some signal into the earth and measure the response, which is the potential difference and also the resistivity value. So the resistivity value depends on what type of conductivity or conductor object is beneath the surface of the earth. But naturally, groundwater is better conductor than other types of rocks, because the groundwater is not a pure, not like like rain and other waters, because it consists of some dissolved ions, and it conducts electricity better than other types of hard rocks. Then I can relate low resistivities to groundwater presence and high resistivities to high density objects or rocks. Then within this, I prepare different types of resistivity maps at shallow depths and again relatively at higher depths. Just this is prepared for shallow depths resistivity values, and it's of course apparent resistivity because I use AB by 2 as depths, and it's not true resistivity, but it can reflect. I can use the horizontal spreads as a proxy for depth. Then from the first shallow depths, I can assume that this is a shallow depth. Then at shallow depths, I can separate the area into at least three regions. The northeast part, low resistivity value. The southwest part, again, another low resistivity value. But this one, which has northwest to southeast alignment, this is high resistivity value in here and in here. So I can divide like zone 1, zone 2, and zone 3. Now there are transition zones here. There are transition zones here, and there are transition zones here. Separations from low to high. Now these transition zones can be different things. Then I wanted to see how it acts along a line. I choose this line. This is a survey line. And I wanted to see how resistivity varies along this line, vertically along this line. Then when I draw the resistivity value along that line, vertically, now the resistivity continues to be low at this place, but varies with depths at several places. Whereas I use again the gravity profile, and when I see the gravity profile at this place is very high, but the other places are intermediate and here is low. Now I got that there is some high conductive object beneath this point. Then I can see that this point is around here. This location is at this location. So, okay. Then I have to take I took another line. Okay, I wanted to see the variation of resistivity with depths along this survey line. And when I observe the variation of resistivity along that survey line, the resistivity varies like this. Okay, it varies, it increases with depths, but the increasing with depths around this place is less, but around this it's very high with depths. So which means that the possibility of having a good groundwater potential zone beneath this place is less, but beneath this place is high. Then with this aim, again, I prepared another map from resistivity, the whole area, the map of the whole area at different depths. Now I use the current spread as proxy for depths. This is not true depths, but it can tell me the relative change with depths. Now at shallow depths, which is the map of, this is the same map like this one. This is the same map at shallow depths. Then at shallow depths, there is high resistive object, which is aligned like this, low resistive areas here and here. And then when depth increases, the northeast part increases like, continues like low resistivity. Again, the southwest part decreases its boundary being low resistivity. Then the low resistivity area decreases, which means the resistivity becomes, increases with depths in the southwest. And then the resistivity decreases along this high resistivity value. So when depth increases up to the maximum depth of my survey, the resistivity completely changes. So at higher depths, what I have noticed at higher depths, the low resistivity area is around this and this one. So what I need is at higher depths, because these are very shallow depths, and the water from very shallow, which means relatively 20 or 30 meter depths, it will not be enough. Or I may not have more than 2 or 3 liters per second water. So I have to go up to the basement rock, which is 350 or 200 up to 350 meters. Then I need the higher depth ones relative to this. Then I use the last depth one, which is this one, and this one maps. So I saw that this area is low resistive and this area is low resistive. Now I wanted to relate this result to that of the first two results. When I come to the magnetic map, I know that this area has some fracture. Okay, and here is also another fracture, and here is another fracture, and here is another fracture. So the low resistivity value is around here. Well, and from the gravity map, I know that the low gravity anomaly is around here. Now the combination of the three techniques confirms me that this area has a very good groundwater potential. This area is the best area, better than any area in my study. Then this becomes my priority. Sorry. So this becomes my first or my first area or my priority area, and then the others around here and here, they become my second choice to recommend borehole for drilling. Then I recommend a borehole, and after combining the results, I recommend a borehole to drill around here and around here. But the local government has a problem for water, and they drill also in other places, which they think is also important. Then I recommend like 3 boreholes, but they drill 10 boreholes because they have a lot of they have problems. Then after drilling, what we have got is they drill 10 boreholes, and after drilling we have got basement rock is at higher depths at this place, which was mapped by my first gravity survey, this one. The basement rock was at higher depths, and the borehole drill at this place yields maximum groundwater, which is 21 liters per second. So the 10 boreholes, sorry, I have to pass to this one. The 10 boreholes drilled. Now, the first one was drilled first before my survey, the red ones, which has 5.6 liters per second. The other 2 boreholes was dry before my survey. And then the local government drilled a lot of boreholes based on my survey. But the best borehole was GW3, which has 21 liters per second. And that borehole is located here. And the combination of the 3 geophysical survey techniques indicates me here, this place is the first and the priority place for drilling. And that result is 21 liters per second. But they drill also other boreholes. other boreholes. They drill like GW2, which is located around here, GW2, and they have got 50 liters per second. And they drill also around here and here, GW1, GW5, and others, GW3, and they have got less than 21 liters per second, but they have got water like 5 liters per second, 12 liters per second, 50 liters per second, and 70 liters per second, but the maximum one was 21 liters per second. So this survey was very effective, and after drilling, you can see people were waiting for water. Now they become stable in the area, and they came with containers to take water from the well. And you cannot imagine how much they were happy. And when they drill water, when the water was pumped from the well, they took water like this, being happy. Now, the survey was very successful that we recommend like 4 wells, but the local government drilled more than 10 wells. However, my priority area was very effective, and it helped us to solve the humanitarian crisis, like the shortage of water in the area. So my result, so in the conclusion, my survey was very, it was very effective, and it solves the humanitarian crisis, which means that simple physics, what we know in high school, can solve a lot of problems in our humanity. And it can also help us to grow in economy if we use it effectively. So just, we know it in high school and in lower grades, but we didn't apply. But if we apply, it can solve our many problems. So thank you very much for your time. And if you have some questions, then the next 15 minutes can be for interaction with the audience. Thank you.
So thank you very much, Mr. Mulugeta. It was really a very nice presentation. And it has got relevance for us also, because at certain parts in India, the situation is similar. There are arid zones, the water crisis is there, and such kind of surveys are required, so that when we drill a tube well, we really get the water. So I have to ask one thing. See, you have done a lot of survey.
Yeah.
So whether it is cost effective to carry out such a survey before we go for drilling a hole? Cost wise?
Do you mean, was it obligatory?
It is obligatory. It cannot be avoided. Yes.
No, I can say no, but you will lose your time, your budget and the time. You know, drilling is very, very costly.
Yeah.
Thousands of dollars for one borehole, and you have to use very heavy machineries for drilling, because you are drilling rock, very hard rock. Then every meter of drilling, you will have a lot of money. You have to budget, you have to have a lot of money. Now, suppose if you don't get enough water, or if your borehole becomes dry, then you will lose thousands, maybe 50 to 100,000 of USD everywhere. So it is a big loss. 1, 2, you will not fulfill your objective, because your objective is to have a water.
Yes.
So unless there is a water, then you will not solve the human problem there. So these things will be solved by conducting survey.
Yes.
So these things make the survey to be mandatory. But if the geology is very easy, which means if you know first, or if you have another survey that the water is at this depth, if you have the information, it's not necessary to conduct more survey. If you are confident that there is water there. Now my area was people and the local government drill a lot of boreholes. Now in my area, in my area on 3 boreholes, but surrounding my area, they drill a lot of boreholes. And they didn't got enough water, and most boreholes were dry. That was the trick. Now, when I use survey, I have got this 21 liters per second yield in the same area where 2 boreholes was dry.
Mhm.
Then this makes mandatory again. But if you drill like simple, like easy geology areas like sediment or some soils and shallow depth wells, you may not need a survey. But for deep boreholes and very complex geological formations, it's mandatory.
Yes.
Okay.
So, audience, do you have any questions? Anybody wants to ask? So I think audience do not have the questions.
So one Dr. Sandrop Deep is talking, but he mutes his phone, so he should unmute his mic. I cannot hear any sound. Yeah, he should unmute his mic.
He is not near to me because he is online, but I cannot see him.
Okay.
Just wait for a minute. I think he may be.
Okay, I am okay. Anyone?
No.
Okay.
So thank you very much, Mr. Mulugeta. Sparing time for us. You have a very busy schedule. You are at the final stage of submission of PhD. Still, you spare time for us.
Yeah, okay.
And really, it was an enlightening lecture for us because the problems which you have discussed, they are relevant for us also. So thank you very much. And I hope you will be in connection with us in future also. And whenever you get an opportunity to visit India, you please come to our college also. It will be our honor to welcome you.
Thank you very much. Yes, I will come one day because we have good connections with India.
Yes.
And we have a lot of PhD students also in India.
Yes.
So thank you very much for your invitation.
Thank you, sir.
For your attention also. And I think I finish before my allocated time. I think you will have like 5-6 minutes before lunch, I think so. Okay, it's my pleasure if you invite me again when you're for your next conferences, similar seminar and conferences.
Yes, sir.
I'll be happy to join you.
Thank you very much, sir. Thank you.
Thank you very much for your attention. Thanks. Bye-bye.
Bye, sir.
Bye.